Welcome to the lecture on embeddings. I'm Nada Wu, a research engineer at Facebook AI Research. I work on large-scale and general-purpose embeddings and entity linking. I also study fairness and biases in NLP models. In this lecture, I will be talking about the following topics. First, I'll start with word embeddings. Word embeddings plays a very important role in NLP and applications. From the last class, you may have learned about LSTM and RNNs. The word embeddings can be used as the initialization of lookup table in LSTM and RNN models. So I will only talk about the high-level ideas around word embeddings, and if you are interested to know more about it, there are great online resources. Next, I will also introduce graph embeddings briefly. Graph embeddings can be seen as a generalization of word embeddings, which also has a great body of work in research and application. Then I'll be focused more on the application side of embeddings. In this part, I will give several concrete examples of how to use word or graph embeddings for different tasks, including ranking, recommendation, classification, and tagging, and so on. The idea comes from the question of whether we can embed everything, like a user or a piece of content. Can we use it to determine if one person is going to like a piece of content or if two people are likely to become friends? At the end, I will talk about some additional topics. I will mention about hierarchical embeddings as well as the issue around fairness and biases in word embeddings. So, in a nutshell, embeddings can be viewed as mapping objects to vectors through a trainable function. In previous lectures, we've learned about neural nets, such as CNN, where it maps an image into a vector in real space. Similarly, we can map other things such as text into a vector. Typically, the neural net can be CNN, RNN, or a transformer for text, or simply a shallow one such as word-to-vec. Here is a picture illustrating mapping different objects into the same space. Usually, the distance between the vectors in the space is used as a similarity function for different objects. For instance, we want to map similar objects closer in the space. In this case, at the upper right, there's a video about a birthday cake, and then it's mapped close to the text Happy Birthday and hashtag I'm old. For the rest of the lecture, we will be talking about how we're going to learn the vectors of different objects. At the end of the lecture, you will have an idea of what are word embeddings and graph embeddings and how they are learned. You'll also learn how to use those embeddings in applications and what kind of task can benefit from it, such as recommendation, tagging, search, etc. You'll also get an idea of how large-scale computing works for learning embeddings.
The search for a good representation of word has been a long-term pursuit in NLP. The idea of distributional semantics is if you know what context to use a certain word, then you understand the meaning of a word. As J.R. first said, you shall know a word by the company it keeps, and it is one of the most successful ideas of modern statistical NLP. When a word W appears in text, its context is the set of words that appear nearby with a fixed size window. And then you can use the meaning context of W to build up a representation of W. So the meaning of the word can usually be inferred by the words surrounding it. For instance, for the example of banking, if we know the context of many examples where banking is used, we can infer the meaning of it. There is a series of work based on the idea of learning word representations using neural networks. The work by Joshua Bengio in 2003, a neural-probabilistic language model, proposed the following. It associated each word in the vocabulary a distributed word feature vector, and it uses a neural network model, essentially try to predict the next word. And later the work by Ronan Colbert and Jason Weston and other collaborators used a convolutional neural net to know word embeddings. The word vectors and other parameters of the neural net is trained on several different tasks, including language model, named entity recognition, and part of speech tag, etc., with sharing the word vectors. And it showed that it's useful for all these tasks. And they also looked at the nearest neighbor of the word vectors and find that it displays syntactic and semantic properties of words. More recently, Tomasz Mikhailoff et al. Proposed a relatively simple model called Word2Vec, which is really efficient to compute, where the word vectors are the only parameters to be learned in the model. Because of its efficiency and powerful performances, it gets wide adoptions in both NLP research and applications. Now I'll introduce briefly about the Colbert and Weston vectors. The idea comes from that a word and its context is a positive training example, and a random word in the sample context gives a negative example. So in this example, the positive example is the phrase cat chills on a mat. And if we take the random word Ohio, the negative example becomes cat chills Ohio a mat. Obviously, that doesn't make much sense. Then the score is calculated by a neural net built on top of the word vectors, and we want to penalize the score of cat chills Ohio a mat, and optimize the score of cat chills on a mat, the positive example. So here we use a margin loss on it. This is similar to the ideas in support vector machine, where you want to increase the margin between the positive and negative examples. It is also noticeable that we only need positive examples in the training, and negative examples are drawn from random words. So in this case, a random word from the dictionary. In the later part of the lecture, I'll talk more about finding negative samples or negative sampling, as it plays a very important role in different embedding models. Next, I'll talk about Word2Vec in a bit more details. The idea is to use word to predict the context words. This is the skipgram model. There's also the continuous bag of words model in Word2Vec, which I'll not cover here. So the context is a fixed window of size 2m. Let's take a look at this following example. So here in the example, the context window is size 2, and we have part of the sentence as problems turning into banking crisis. Assuming the word into is the center word, so we hope to use the vector representation of word into to predict what would be in the context of into. We try to make those predictions and change the vector representations in a way that we can do the prediction better. Similarly, we go on to the next word, banking, and essentially we'll do the same thing. More formally, we write down the following formula as skipgram objective function. For each position t, predict the context words within a window of fixed size m, given the central word wj, and we multiply all those probabilities to be our likelihood. And here theta is all the parameters to be optimized. So the objective function is the average negative log likelihood. Note that in this particular model, the parameters to optimize are only the word vectors. And this is simpler than the earlier neural net models, and also it enables very fast computation. The question then becomes how to calculate the probability. In word-to-vec model, it proposes two vectors to represent each word. One for when the word is a center word and one for when the word is a context word. Then it uses inner product to measure how likely word W appears with context word O. And if the inner product of these two vectors is bigger, the probability is bigger. And if the inner product is smaller, then the probability is smaller. So this is the softmax form that we've learned earlier in the class. And the probabilities falls within the range of 0 to 1 and sums up to 1. And the two sets of vectors are all the parameters in this model. So we can do stochastic gradient descent on softmax function. But the problem is that it's very expensive to compute because the size of the vocabulary is very big, usually tens of thousands or hundreds of thousands, make it impossible to compute. So there are two solutions. One is to use hierarchical softmax, and the other is to use negative sampling. There are other family of word embeddings which also have been widely used. They differ in several aspects such as algorithms, text corpora, dimensions, etc. For instance, GLOVE, where the training of the embedding is performed on aggregated global word-word co-occurrence statistics from a corpus. And FastText, which is also from Facebook AI and has wide adoptions, it adds subword information in addition to word-to-vec, which better handles out-of-vocabulary words, and is also available in more than 200 different languages. It's shown to be very efficient for text classification tasks. So you can find those pre-trained word vectors through the links here. And a common way of using the embeddings is to use it as features in downstream ML models or as initialization of neural net models for NLP such as RN and LSTM, and finally, more recently, the contextualized word embeddings has become very popular, such as Elmo and BERT. So it will be covered in detail in later lectures. Now I want to talk about how to evaluate word embeddings, as evaluation is always a very important part. There are mainly two categories of evaluations, namely intrinsic ones and extrinsic ones. In intrinsic evaluation, word embeddings are usually evaluated on a specific internal task, and such as checking the nearest neighbor of a particular word vector. And it is usually fast to compute, so you can check the quality of the word embeddings during training, and it helps you to understand what the model is learning. However, it is not clear whether it really helps in real tasks. And on the extrinsic ones, it's usually evaluated on a real task, so it can take a long time to compute. And another issue is if the result is not as good, then it's unclear if the problem comes from the word embedding or from the interaction of the word embedding and other systems. So a common way of solving this is to keep the other parts fixed and only change the word embeddings. If that improves metric, then it usually tells you that the word embedding is of better quality. And we also use this approach for evaluate other embeddings, such as graph embeddings I will talk about later. One interesting example of intrinsic word embedding evaluation is the word analogy task. In this task, we have a pair of word man and woman, and also a word king. We wanted to know which word to king had the same relation as woman to man. We observed that the trained word embeddings have the following property. Evaluate word vectors by how well the cosine distance after addition captures intuitive, semantic, and syntactic and analogy questions. If you find the vector that satisfies the formula on the right top, you will find the vector as queen. This is really interesting as you can find this type of relation by simply doing additions and subtractions of the word vector. There are more examples in the following links that you can try to find out. For extrinsic evaluations, I will give several examples in the application sections. Graphs are networks of entities and connections between them. They can be used to present stuff like protein structures or map data or networks of people's interactions. Multi-relation graph embeddings are typically studied in the context of knowledge graphs. So you can have these graphs of structured Wikipedia data like Freebase that encode facts about the world. And there are other similar graphs like word ontologies. There are also related areas of study such as a recommender system and embedding methods like deep walk that were primarily designed to operate on social graphs. From last section, we talked about word embeddings, and you can think it as defining a graph where each word to be a node and the node has an edge to its context word in sentences. And word embedding models like Word2Vec are essentially learning the embeddings of the graph node, which is the word. Let's take a look at an example here. This is also known as matrix completion, where you have a big matrix and you know some labels between persons and items. For instance, you know that person 1 likes item 2 and do not like item 1. There are also some missing entries in the matrix. We know that there are relations between items and people, and the items can be people, can be movies, pages, articles, products, word sequences. And you like to predict if someone likes an item or a word will follow a word sequence. So you can learn the vector representation of people and items here such that some simple form of the function between these two vectors will fit the existing value in the matrix and predicting the unknowns. So that is a particular case that we want to use graph embeddings for. So what is graph embedding? Here we define embeddings as a node map from entities to vector of numbers that encode similarity. A mapping is just an algorithm that converts entities with relations to vectors or features that encode similarities. For word embeddings, you learn features such that the features of a word is similar to the features of a word surrounding it. For graph embeddings, you learn features that connected nodes are more similar than unconnected nodes, and you learn these embeddings by optimizing this objective by stochastic gradient descent. In other words, we are talking about graph node embeddings here, and note that you can also do path embedding and graph structure embedding, which we will not cover in the lecture. Just as word embeddings, graph embeddings are a form of unsupervised learning on graphs. It can be used as task-agnostic entity representations. The features are useful on downstream tasks without much data, and the nearest neighbors are semantically meaningful. Now I'm going to introduce a particular family of graph embeddings. This is from the open source project PyTorch Big Graph that I worked on with Adam Luria and others. So we implemented several graph embeddings algorithms in a large-scale setting. Here I'm going to talk about the family of graph embeddings that we support in PyTorch Big Graph and essentially the way that we train those embeddings. So given that we have a multi-relation graph like the one on the left, where different colors of the edges representing different relations, we want to optimize the loss function L such that for a simple function of an edge E and a negative sampled edge E prime, we want to minimize the margin loss similar to the loss in the Colobel Western vectors, if you remember from the word embedding class. So the simple function f can be what we learned in the word embeddings, such as the dot product or cosine between the two vectors of the nodes of an edge, except here we add a transformed version of the destination node of an edge to represent the type of the edge. So theta s is the source vector, and theta d is the destination vector, and theta r is the relation vector. In addition to the node vectors, we also learn parameters of different relation types of the edges. So the negative samples are constructed by taking a real edge and replacing the source or destination node with a random node. This again is similar to the negative sampling technique for word embeddings, if you recall. Let's take a particular edge here as the edge B2C. So essentially, the loss function is saying that we want the distance between the vector B and the transformed vector of C to be close, and the distance between vector B and the transformed version of A and E to be large, as there's no edge between them. Similarly, we do this again for positive edge B2C and negative edges A2C and D2C. So the loss can be again optimized by SGD, and this is how the graph node embeddings and parameters of the relations transformations learned. So here are the different types of relations that we support in PyTorch graph. The first one is identity, where we treat every edge to be the same. This falls into the case where all the edge is the same type in the graph. The second one is a translator, where we use a vector to represent a particular edge type, and then we add the edge type vector to the node vector. This is from the TransE model by Borders et al. 13. So we can also do a fine translation where we have a matrix A and a translator vector delta for each edge type, and we do multiplication of the matrix A and node vector plus the translator. This is from Nico et al. 11, where it allows more complicated transformation than the translator model. It also has more parameters to be learned. And then we could also have the diagonal transformation from Yan et al. 15th, where we have a vector B for edge type, and we multiply each dimension of B with the corresponding dimension of X.
What can we do with the learned graph embeddings? Here is an example from embedding a knowledge base. This is from Borders et al. 13, the TransE model. So we have a subgraph from Freebase where it has the entities like Clooney, actor, male, and the relations between the entities. You can learn a graph embedding on the knowledge graph. Then for a question like, who did Clooney marry in 1987? You also have embeddings of the question through the word embedding table. You can then detect the entity in the question and find the corresponding entity in the Freebase subgraph and to find the relevant entity to answer for this question through the entity embeddings. So that's the high-level idea. So again, we're going to talk more about examples of how to use graph embeddings in the application section. So let's take a look at two-dimensional t-SNE visualization of the entire Wikidata graph from the PyTorch Big Graph project. So we follow the method in TransE, but we scaled it to 55 million entities and 3 billion edges with 5,000 different relations. So this is a huge graph. The picture on the left is the visualization of the top 500 popular entities on Wikidata projected in 2 dimensions. As you can see in the graph, we have several clusters, which is quite meaningful. For instance, the numbers are clustered together, and from the top cluster in the middle, you can see different occupations. And there's a cluster of countries on the left bottom, and the entity embeddings learned on the knowledge graph exhibits certain behaviors in the vector space, and you can usually find meaningful clusters. We will see those properties again in the applications section. So in order to train embeddings fast on a giant graph like Wikidata, which I just showed you, we need to optimize a lot of things. One thing that is particularly helpful is what we call optimized negative sampling. So recall in the previous section that we talked about sampling negative nodes to construct fake edges. So the training time is dominated by computing the scores for fake edges. So how can we speed that up? So what if we cropped a sub-batch of 100 edges with the same set of random nodes? So in other words, when you do like batch training, you use the same set of 100 edges without redoing the sampling. This obviously reduces random access memory bandwidth by 100x. And if the similarity metric is dot product, a batch of negative scores can be computed as a matrix multiply, and that further could help in efficiency. So we find this trick to be really useful in practice, and the graph on the right shows how you can increase the number of edges processed per second with doing the batched negatives comparing doing unbatched negatives. We also build techniques to enable distributed chaining for graph embeddings. That further enables us to train really giant graph embeddings. I'm not going to cover the techniques for distributed training in this class, but you can check out the PyTorch Big Graph project.
So far, we've learned about word and graph embeddings in Euclidean distance. More recently, there is an interesting body of work on hierarchical embeddings. For instance, the work of Maximilian Nicol and Dao Aquila in Europe 2017 learned hierarchical representations by embedding entities into hyperbolic space using Poincare distance. So the key idea behind is with the natural geometry of the hyperbolic space, the embeddings learned discovers hierarchies from similarity measurements, which often exists in data. For instance, if you check the graph on the left, you can see that vector of more general category entities, such as the name entity, is very close to the center of the space, where a more specific term like sperm whale is far apart from the center. So additional benefits of the hyperbolic embeddings is that it usually requires far less dimensions to represent those entities. For instance, dimension people usually use for word-to-vec is about 300, while in hyperbolic space, usually a dimension of 10 is good enough to learn good quality embeddings. You can also infer hierarchical relationships from the embeddings. You can find more about this work from the GitHub link on the slide. Another topic I like to cover briefly is the issue around ethnic and fairness in word embeddings. We will have a lecture on fairness entirely later in the class, so here I'm going to talk about it very briefly, and you will know much more in the later lecture. So machine learning systems are found to be systematically biased. Not only the bias comes from the dataset people used to train ML models, but it is usually the case that the bias is further amplified by the machine learning system, which can cause lots of issues. As we rely on ML systems heavily these days, it is very important to make sure that our ML model do not exhibit or amplify existing discriminatory or unfair behaviors. In the case of word embeddings, it is known that trained embeddings such as word-to-vec exhibits those kind of biases to some extent. In the work of Balukbasi et al., they showed that in the word embedding space, the relation reveals that man is to computer programmer as woman is to homemaker. It also showed extreme she occupation versus he occupation. As we can see in the list, the nerd model exhibits existing biases towards occupations for different genders. In their work, they also discussed how to debias, and it is not an easy task. Here's an overview. First, we identify gender subspace with gendered words. Next, we project the words onto the subspace. We then subtract those projections from the original word. This is illustrated by the picture on the right. And there's still a problem with it. First, it is not that effective, as male and female words are still clustered together. Second, bias pervades the word embedding space, and it is not just a local property of a few words. There is a rich body of work studying biases in NLP models and debias techniques. Please check out the lecture on algorithmic fairness to know more about it. In this part, we are going to talk about applications. First, let's take a look at a simple application which we call it tag space. In this case, you have posts with text like restaurant has great food and hashtags like yum and restaurant. You wanted to infer proper hashtags for text without hashtags. So this is quite similar in the word embedding case, where in additional to words, we also embed hashtags. You can have edges between words and hashtags given those words and hashtags appear in the same post. and learned embeddings for both of them. Then you can use the embeddings to label the posts and to do hashtag clustering. In the case of page space, we have users follow certain pages on Facebook. The pages can be celebrities, restaurants, coffee shops, and organizations. We can see this defines a partial graph between users and pages, where the input is user page pairs. Recommending pages for users to follow can be viewed as predicting missing edges in the graph. We use this information to embed pages to form a space of page embeddings. And you can also use to do clustering of pages and recommending pages to users. We use this for users. It's being represented as the collection of pages for the pages that they followed. The benefit of doing this is we do not need to embed every user, which will be a big computational requirement. It also better addresses the cold start problem. So for new users without much information, it is harder to train good quality embeddings. But because of the pages are relatively well trained, we could use that to get a reasonable user embedding. So you can find more about this on the GitHub link on Starspace, which is an embedding library that is convenient to use. Here is an example of learned page embeddings. If we search for nearest neighbor for the page The New York Times, we can get pages such as Washington Post, Bloomberg Politics. They are all close in the embedding space, and obviously we can use it to recommend users who follow the New York Times other similar pages. From a practical point of view, how to search the nearest neighbors efficiently from millions, even billions of vectors is a very important issue. So for this, we use FICE, which is a library developed by Facebook AI for efficient similarity search and clustering of dense vectors. This really enables retrieval by dense vector feasible in production setting, and it powers our product on a daily basis. Now, we only use the user's engagement data or behavior data for learning the page embeddings. We haven't used any content information yet. So, for instance, the title and description of the page often tell you a lot, and the images or videos posted on the page is also informative. As in the next example, I will talk about how to combine different types of information and map entities in the same space. In the example of video space, we start to consider more relations and information in the graph. We have pages which publish videos. The video contains words in its title and description, and we also have visual content. We also know information about the video. For instance, certain users have engaged with the video, and we have human labels on the topics and subtopics of the video. Now, we would like to get a representation of the video by the following. First, for pages, we have a giant lookup table initialized with the trained page embeddings. Similarly, we also have a word lookup table and word embeddings, and we aggregate all the words in the title and description as the text representation. For visual content, we took snapshots of videos as images and fed it into a classic visual model such as CNN and used the last layer of each image as the visual embedding. Finally, the embedding features are fed into MLP with other features on top. Now, if we use it for classification, such as to predict the topic of the video, we add a softmax for multi-classes classification. And if we use it for recommendation, we use ranking laws as similar in the page space case, where it is good at capturing partial information. The entire system is trained end-to-end with stochastic gradient descent.
So from the video space example, we already seen that different behavioral data and content data is helpful for a bunch of tasks. So what about the idea that we just embed everything into vector space? So this leads to the idea of world to vec, where world is everything and we want to embed them into vector representations. So here is a simplified version of world to vec, where we have the graph. In the center, we have users engaging with pages and groups and posts, and pages can create posts and link from different domains and so on. So again, this graph is huge, especially if we want to embed every user in the graph. Embedding all these different entities in single space is pretty powerful because you can say things like which topic is the user interested in, or which topic does this post belong to. You can also use these embeddings for some other task that has very little labeled data. Like suppose you have a list of 10 videos that's in French and want to find more videos in French.
Here is an example of behavioral data on the right. If we can take this behavioral graph and convert it into features that describes the similarity of all these entities based on their interactions, we can use traditional machine learning systems to answer lots of important questions, such as what pages or topics might you be interested in? Which posts contain misinformation, hate speech, election interference? And is a person's account fake or hijacked? And what sounds might you like, and even if you've never provided any sound information before? Once we have embedded the giant graph, what can we do with it? Here's an incomplete list. For users, we can use it to detect bad actor, where bad actor is defined as people who post malicious content. For groups, we can use it to identify certain category groups such as for sale. As for this type of groups, users usually engage with it in a certain way. For pages, again, we can do recommendation, category prediction, and identify spam and hateful pages. For domains, we could predict the domain type and identify misinformation. Let's take a look at a visualization of the embeddings of the behavior graph on the right. This is using t-SNE, which is a widely used method for visualization that itself constructs an embedding in low dimensions. In this case, an embedding into two-dimensional space. So here we mark the pages that's misinformation in green. Here's a few things to note. First, the graph embeddings didn't know anything about misinformation, but misinformation pages clustered together in the space. Second, because the graph embeddings don't know what they're looking for, you will still need to put a model on top of the features, but you can train with any kind of machine learning model on top of these features like neural network or random forest, and it will be very predictive, and you can combine it with other information you have.
Here is a summary of word2vec. We take a giant behavior graph with different types of entities and different types of interactions between them. We use unsupervised graph embeddings to convert them to node embeddings. Then possibly we combine them with other features such as content features, counters, etc. Then we use it for all different kind of downstream tasks such as ranking, classification, clustering, finding nearest neighbors, and so on.
Let's dive in a bit deeper in technical details. We released the platform we used to train World2Vec, which is the PyTorch Big Graph library I mentioned earlier. Now let's go through the overall workflow of training a giant graph embedding model. As the first step, you need to prepare the line graph. That's going to be a list of IDs of the source, destination, and relation types. Then you feed it into the PyTorch Big Graph workflow, which does some pre-processing in the database to shard everything. Then you run the PyTorch Big Graph open source code and then do some post-processing. So you end up with a database table of IDs and their embeddings, which you can use in all different ways as mentioned above. For example, people use it a lot to look for nearest neighbors. So this supports very large-scale computations, and I want to show you some techniques on how we scaled the graph embedding training algorithms to handle really big graphs. So the key idea is to partition the graph. We use matrix blocking to subdivide the graph. First, we divide the nodes uniformly into n shards. Then, according to how the nodes are divided, the edges between the nodes are divided into n-square buckets by the source and destination node. So the benefit of partitioning the graph into smaller chunks is that we could handle one chunk at a time. In the single machine training, we only take one bucket of edges and then train on those edges. So only two partitions of the model are held in memory and others are swapped to disk. This could save a lot of memory usage and allows it to train really big models. And in the distributed training, buckets with disjoint partitions can be trained simultaneously without synchronizing model parameters. So this allows us to train the model in parallel with multiple machines and be really efficient.
Here is the overview of the distributed training system. It requires several types of communication. First, you need to synchronize the bucket access, and you need to exchange model predictions once you've done training a particular bucket. There's also some common shared parameters across different machines. Those are the parameters of the relation types, and it's stored in a shared file system. Because of the number of shared parameters is relatively small compared to the giant embedding tables that we are learning, this scales almost linearly by the number of machines or trainers in the system. So if you train this on, say, 40 machines, you almost get 40x speed up with much larger embedding tables as well. So overall, this enables us to train on giant embeddings efficiently.